ladies and gentlemen. Great to have you here in our, here again in our public online lecture series on sustainability in computer science. Our speaker today is Professor Ivona Brandic. She is chairing the research unit on computational sustainability. It fits to the topic of her presentation. And she is co-chairing the Doctoral College on Computational Sustainability, which TU Wien, together with Johannes Kepler University of Linz, just started half a year ago. And I think the first call for the doctoral students just came out this week. So it's really very timely. The topic is hot, and Ivona, it's your floor.
Okay, hello. Thank you, Gerti, for a very nice introduction. Hello, everyone. I'm very happy to be today here and also to present you concept of computational sustainability, and I will give a brief introduction to the topic and also to try to give you introduction to the topic from very different angles that we have in computational sustainability. So let's start. We all know and we all use computational power today, and computational power has revolutionized more or less the way how we do science, how we approach our life. Today, I just was last week in Graz also discussing about virtual vehicle and what can we do to simulate trains, cars. Well, we can do a lot of things today. If you want to understand what happens if two cars crashes, you don't have to crash them. You can create simulations, and you can create finite element simulations and repeat it and study it. It's cheaper, it's reproducible. You can do it many times. You can fine-tune some parameters, and if you try to fine-tune specific parameters, then we speak about the optimization. And in the past, we had very analytical approaches. So most of the approaches were analytical. Today, we have data-driven approaches, no matter whether we are talking about DNA sequence analysis or genomic sequencing of SARS-CoV-2 virus, large language models, recommendation engine, and so on and so on. We have data-driven approaches. The downside of this development is shown in this figure. You can see it where Emma Strubel et al. Created a comparison of our everyday activities and CO2 footprint of our everyday activities compared to a CO2 footprint of different AI models. You can see here different activities, and here you can see the CO2 emissions. We have here the CO2 footprint of an air traveler from San Francisco to New York, CO2 footprint of a human life, CO2 footprint of an American life. Then we have a car with fuel during a lifetime. We have training one deep learning model with pipelines, with parsing, tuning, and experiments. And we have transformers with neural architectural search. This is, I think, quite old. It's from 2019. There are newer numbers. There are also different other experiments, but I'm showing this picture because on the, how to say, intention and on the scales did not change much. There are still such numbers, but yeah, relations maybe today a little bit different. So all these developments led to the development of a new research field, which is called computational sustainability, that target different methods that we can use to control, maintain, visualize, resource consumption of IT, but also to study, to understand, to influence how people use IT in order to, I would say, build a better world, right? How to use IT to save our world. And we have here different methods. I'm using in my research all three of them. So usually in computer science, we have very common method, which is called trade-off. Means you have different dimensions, very common in software engineering. You have maintainability, modularity, accuracy, usability. So you usually trade one of those dimensions to do optimize one of the other dimensions, right? So you give up a little bit, I don't know, security for the better efficiency. So this is what usually happens in computer science. Another method that we have here is called disruptive, means every now and then we have inventions in computer science that disruptively change the way how we do computing. One example is invention of smartphones. Another example is invention of internet. Yeah, they don't happen very often, but they happen, and they completely change the way how we do computing or how we communicate. And then the third method is behavior change, means how can we influence people and how can we influence their behavior in order to use IT in another way, to use it in a more efficient way, or to use less resources, less computing power. I'm going to talk about all of them. And we have always the actors that cannot be seen and cannot be examined in isolation. We have IT. In order to operate IT, we need humans. In order to operate IT, we need nature. We need electricity that is produced using, I know, wind or water. And they do not happen in isolation. They do not exist in isolation. And this is, I would say, yeah, on a big in a very coarse-grained context, the subject of computational sustainability. And as I said, I work in all of these areas. I have put some of the projects that we currently have. They somehow navigate from how we can build a better future, how can we protect our environment with IT, to how can we create disruptive changes. In particular, I'm focused on non-classical computing, where we use, for example, quantum computing to do more efficient computation. And there is also here also different trade-offs, technologies, and different trade-offs, methodologies in order to achieve better computation and more efficient computation. I do also some research in behavior change, not much, but still I do it. And I don't do it alone. We have partners who help us to talk about live research. You know, I don't want to leave this field to influencers. Every time I don't say something, someone else is going to say something about my research field that is maybe not that competent as I am. So we try also to speak about the topic, and not always in a very, how to say, concerning manner. We try to be also in an entertaining way, so that people perceive it easier, especially if you talk to young students and kids. So we have collaborations with Austrian Academy of Sciences, where we created different YouTube videos. They created with us also shorts on TikTok and so on, to explain the ICT consumption and energy consumption of ICT. And in order to do that, we also created different analogies and metaphors to allow people to perceive the resource consumption, because sometimes it's not really easy to grasp what does it mean 3 kilowatt hours. But if you say, one load and fully loaded dishwasher operating, so people can grasp what it means, and this is equivalent to energy consumption you need to generate 1,000 images. Or for example, if you say half a liter of water is what you in average need to create 5 to 50 prompts with ChatGPT, depending on where you are on this earth and depending on how hot and how cold it is. So this is how we also try to communicate and also talk about this research so that everyone can understand it. And just recently, there was a big ongoing discussion in media everywhere, because Sam Altman said that OpenAI pays several $million every year just for politeness, because people are too polite to ChatGPT. And also in Austria, media was quite interested, and I also gave interview about that. Yes, this is also a big issue, because the way how we use this technology is now allowing everyone to use it. So of course, computer scientists could use it efficiently because we know how programming languages work, we know how to structure, we know how to efficiently speak, most of us. But now the way is, how can we educate everyone to use such technologies in a, let's say, efficient way? And there are several measurements, for example, from researchers in Canada. They have really measured the energy consumption to process a specific amount of tokens that they can map now to this politeness. And we are also having PhD position in doctoral college on computational sustainability. I'm working together with Martina Mara, and we are trying to explore green prompting strategies and eco feedback for efficient use of large language models. So there will be a dedicated position on this topic. And Martina is specialized also on this interaction and how human interact with IT facilities, right? So if you are interested to work in this area, feel free to apply, because I think the position is still open. And it's going to be at JKU in Linz. Okay, so let's look now into the trade-offs. And the trade-offs are very, 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 I would say, standard method to achieve sustainability. And here you can see different pictures of myself that I did when I was visiting different data centers. Don't ask me why I take pictures when I visit different data centers. And you can see that not much change in data centers. We have servers, we have cables, we have power units, power sockets. We have a lot of cables here, a lot of cables there, and did not change much in the last, I would say, decades. However, if you look now at the outside of the data centers, you will see that many things change now at the outside of the data centers. So now if a superscaler build a data center, they usually buy a power plant. In many cases, not always, but in many cases, it is now a nuclear power plant. And then there are also now intentions to develop small modular reactors that can be put in a plug and play manner into the data center and secure energy supply of the data center, regardless of the environmental conditions. However, what we try to do here, we try to understand how costs of a data center behave depending on the let's say, cost of intelligence or the scale of the intelligence. So what you can see here on this diagram are the large language models measured in billions of parameters. And you can see here we measured the energy per token in watt hours. And you can see here that the behavior here is linear. So the cost of intelligence increases in a linear way here. So, and we try now to take advantage of this development and to understand how code generation can be improved by exploiting this linear behavior in the cost of intelligence. And code generation, apart from the natural language processing and what we all use with large language models, is one of the very important areas. Today, code assistants are widely viewed as the future of software development, and studies report that 30 to 40% of code in large organizations is now AI generated. So it's quite, I would say, interesting to look into that and how can we fine-tune energy consumption of code generation. And we developed resource-efficient inference in LLMs. So how can we fine-tune LLMs? Well, they are, I would say, well-known methods if we want to fine-tune LLMs. One of them is well-known, I would say, known in machine learning in general. Knowledge distillation refers to process of transferring knowledge from a large model to smaller one. And in a large models, such as very deep neural networks or ensembles, they possess higher capacity to represent knowledge, but sometimes those knowledge is not necessary. So it and it's just computationally too expensive, right? Then we have quantization. In quantization, we try to make smaller, faster, more efficient models by reducing numerical precision. And then we have also compression. However, code is generated in a dynamic way with different degree of complexity in each line of code, and we need to understand the input context code file and choose the corresponding inference load dynamically. So this is knowledge distillation, quantization, compression is not always the right way to do that. So what we have done, and this was also published in last CC Grid conference in Tromsø, we analyzed the behavior of large language models in regard to the exit index, means the exit index of the neural network. You can have 10, 20, 25, I don't know how many layers of neural networks. So also here we have linear behavior, means the total energy based on the exit index increases linearly. You can see it here on this diagram. However, if we look into the quality of the generated context, in particular, if we use code generation, you see that the first layer contributes significantly higher to the quality of the generated context than the later layers. And you can see here different benchmarks. For example, Rouge is used, Rouge-L is used to describe quality of the summaries. So if you have text and generate summaries of the text, code blue and blue are used to generate the quality of the code generated. And we developed a new approach using reinforcement learning and different other techniques to identify the index layer where you should exit, generate the code and exit and omit higher layers, because here you have, for example, at layer 17 or 18, you have quite high quality of code generated, but you save up to 30% of the energy because you just skip those layers, right? So this was one of the very interesting outcomes of this study that we conducted together with Shashi Ilaga, who is now a professor at University of Amsterdam. So this is the part on the, and this research or similar research, like this transprecision, where we trade different dimensions, is part of my FWF project, Transprecise Edge. And there is also another project where we deal with trustworthy and sustainable code offloading between different entities that are geographically distributed or have different architectures. Okay, now I would like to look into the second part of my talk, where I'm going to talk about the disruptive methods. And as I said, disruptive methods means something completely different in terms of how we do computation. And nowadays we have upcoming and we have a new technology, a new architecture in computer science that is based on quantum computing that promises us way more efficient computation than on the classical architecture, or that promises us to do computation that is simply not possible to be done on the classical machine, right? So here is just one example. If you try to represent the energy configuration of a single caffeine molecule at a single instant, it requires you approximately 10 to 48 bits in a classical computer. You can do it on the quantum machine with 160 logical qubits. This is just to show you the dimensions we are talking here about. And this characteristics is called space efficiency, means you can do way much more computation on way less computational resources. So very broadly speaking, right? And then there is also a very interesting quote: every time you add a qubit, you double your possible outcomes. With 20 qubits, there are 1,000,000 possible outcomes. With 100 qubits, you have more possibilities than there are bits in the hard drives in the world. And with 300 qubits, that's more possibilities than there are particles in the universe. Good. Well, so what can we do with that? It allows us to do computation in a different way. I'm not going to talk now about the basics of quantum computing, but about the possibilities that we have here. Instead, 0 and 1s, we have so-called qubits, where the computational basis in a superposition means 0 and 1s at the same time. But once we measure it, this complex amplitude collapses into its bases into 0 and 1s. You don't have to be expert here to understand, okay, this structure or this computational basis can allow me to represent maybe molecules in the better way, or if I represent molecules with qubits, I can do some computation way easier. For example, calculate the eigenvalues. And this is also one possibility and way how we use quantum computer. And I think it's also, there is not much that you can understand in an intuitive way about quantum computing. This is one of the very, very, very few things. And that's why I'm using this to explain it to you. So we have here a bottom-up approach where we, for example, represent a native 3D modeling of scientific application through qubits and quantum computing, and where we can do, for example, calculation of quantum eigenvalues, or where we can implement variational quantum linear solvers here based on this computational basis. So what is the idea now here? As you can see here, you can do linear algebra very well here. But if you want to do arithmetic operations, probably quantum computer is not going to help you very much. So that means we have to combine this powerful quantum computer that can do linear algebra for you, very powerful, in a very powerful way, with a classical machine that do other things that quantum computer cannot do for you. And today we combine quantum machines with classical AGPC cluster to do many tasks on the quantum machine that quantum machine cannot. So from the architectural point of view, we see such HPC cluster as a batch system where you have a front end, you have your SSH terminal where you log in, compile, upload your file, upload your data, submit your jobs. We have a data center with several nodes. Each node has its own operating system. Nodes are interconnected with network cable, higher performance, demand more processors, and we share it with many users. Now, if we have a specific user A gets certain node reserved where he can do the computation. Then the second user gets another node reserved where she can do the computation. The third user gets 3 nodes where she can do the computation and so on. The idea here is now these nodes might be already quite heterogeneous in the classical data centers. You can have GPUs, CPUs, TPUs. The idea here is now to integrate a quantum machine where the batch system can direct specific tasks, specific computational tasks directly to the QPU that runs on the quantum machine, and you do your linear algebra there. Okay? The idea seems very simple, but it isn't. In practice, it isn't. We have developed one of the first hybrid machines in this world. There are very few such hybrid machines in Europe. I think in Munich is one. There is one in Lumi, in Finland. In Barcelona, I think there is another one. There, in Jülich is also another one. And we have one in Innsbruck. So in Innsbruck, we have a classical machine, classical HPC cluster. And we have also ion-trap quantum machine. And they are integrated through a GPC node where we have login console, where we have circuit API, for example, Qiskit, and where the user from this AGPC node can access offloading APIs and use quantum machine in order to partially process data here, but also partially process data here on the classical machine. We have implemented in my group different hybrid QLibs libraries, and we have benchmarked different use cases in hybrid infrastructures. In particular, we did the first benchmarking with molecular dynamics. I already told you. Native 3D representation of scientific problems is one of the use cases. But what we are also doing is quantum machine learning, the quantum version of classical machine learning that is used for training and also for inference on the quantum machine, which is also another use case. And I have a very successful team, I would say, and this is just, there are just the awards that they got, I think, in the last, 12 months in regard to the hybrid classic quantum machines. But you have also to understand there is not just a quantum machine that I can order and buy somewhere. So someone has to build it for us. So this is the process of assembling a quantum processing unit in Innsbruck that our colleagues did for us. And I say did for us. Why? Because they want us to do some computation on this quantum machine. So what they had to do is, for example, they had to change isotope from calcium to barium. And they told me they did it because if they use barium, then the excited particles stay in an excited state a little bit longer for a few more nanoseconds so that we can measure it, right? So they had really to adapt and fine-tune the parameters, for example, the 2-qubit error rates, initial error, readout error, to specific order of magnitudes to be able to do some computation on this machine. Otherwise, you have just the noise and you can do nothing, right? So there is a lot of, craftsmanship, yeah, when you build such machines. And the machine is also put into the rack. So this is the machine, the ion trap machine, and the machine fits into the rack, which for me, as a high-performance computing professor is something very revolutionary because the machine works on air, on a room temperature. So you don't need here cryostats, you don't need this big fridge. that you have for other types of quantum machines. And it fits into the rack. So it fits very nicely into these units that you have in a data center. And this is the ion-trap machine operating in Innsbruck. Yeah, the blue color is because of barium, I was told, right? Good. So what can we do now with this machine? I already mentioned we are using it for quantum machine learning. So how can we do that? Well, this is not so straightforward because there are issues to be solved. And one of the issues is that once you, I mean, there are several issues with quantum machines that are very, how to say, difficult to comprehend. For example, you cannot copy a qubit. So it makes the simplest algorithms that we have in computer science not implementable, right? You have to find other ways. Another problem that we have here is destructive measurement. That means once you measure the state, it destroys, you destroy it. The quantum information is destroyed due to system collapse, right? This collapse destroys any quantum information previously stored in the qubit's wave function. And as a result, the measured qubit cannot be reused for any further quantum computation without being reinitialized. So the destructive measurement is something very expensive, very unpleasant in this setup. And then there are ways how to overcome or how to minimize the number of these destructive measurements. One way is, this is also done by Richard Küng in Linz, are classical shadows. This concept of classical shadows means that in a quantum computing, you try to summarize and compress the information from quantum state into classical representation. And instead of performing a full quantum state tomography, which requires exponentially many measurements, classical shadows can do it and estimate many properties of quantum states using only polynomial number of measurements. That means you have your randomized measurements here at a specific time slots, you do the measurement, and then you have the classical processing where you, based on this strategically selected measurement, try to reconstruct the state, where you can then estimate the state fidelity, entanglement, entropy, correlation function, and all other things that you use for computation. So the concept here is you have this super efficient quantum machine, but in order to use it in an appropriate way, you have to use very often the classical machine to get this randomized measurement. Means the role of the classical machine is here very important and can represent a bottleneck in the computation and communication. But these shadows, classical shadows, represent also a building block for development of quantum neural networks. And as I mentioned, besides native representation of scientific application like molecular dynamics, you can use also quantum neural networks with quantum circuits, with tunable parameters like rotation, angles on quantum gates to process input data. So you have here your input data, and these parameters are adjusted just like weights in classical neural networks to minimize the loss function, right? So here you have the representation of data input, classical computer and quantum computer. So you can see here just from this picture, so here is the initial parameter data, encoding, selection of the circuit, parameterized function. So you execute your quantum computation based on this set of parameters that encode your physical phenomena. You evaluate if it's satisfying. You try to change your parameters, do another computation, evaluate. If it's not satisfied, you change the parameter and so on. You iterate until you encode your problem or represent your problem in the proper way. So, and you can also see here the role of the classical machine here, which is here very, very, very interesting. Why? You can now represent. You can now imagine the learning of in QML also is a kind of a graphical representation with a landscape where you try to reach certain efficient states, right? You want to optimize learnability, trainability, expressibility. And in best case, you start somewhere here, you start with your optimization, and then tack, you are here and you get what you want. What usually don't happens, so usually you start here, your gradient of the cost function with respect to the circuit parameters becomes exponentially small as the system size increases. The training of the model is extremely difficult as gradient-based optimization stales, similar to being stuck on a flat, featureless desert with no clear direction to go. So you wander around in this optimization landscape. And the worst thing here is you have this super efficient quantum machine, and you burn energy, you burn resources with a classical machine in order to let this machine do something. And you don't know which exactly direction you have to go. And this is the problem, this is the dilemma that we have currently, that your training might fail, gradient descent becomes ineffective, especially as the number of qubits increases. You waste resources, you run quantum circuits that don't contribute to learning, you waste time, you waste quantum computing resources, and it is hard to train larger QML models. So this is also the subject of another PhD position that we have in doctoral college on computational sustainability, where we want to understand the role of the classical machine in order to steer the quantum machine. You need it to load the data, you need it to do VQE, you need it to recalibration, so many other things. So we want to understand what are the resources that we use on the classical machine to run this super efficient quantum machine. Okay. So, and this project is also part of the Doctoral College on Computational Sustainability and supervised with Richard Küng and Vincenzo De Maio. And if you're interested, feel free to apply. The position is located at TU Wien. Good. And now the last part of my presentation is about how can we use IT to build a better world. Maybe you know this picture. The picture shows Batagaika crater. This is in Siberia, and in Siberia we have permanently too high temperatures so that permafrost is thawing. And so like snow is melting here in Austria in spring, the earth is melting in Siberia with many side effects, with many problems that results out of this. One of the follow-up problems, I mean, this Batagaika is not inhabited, so there are no people living, but this permafrost thawing happens also in inhabited areas, for example, in Norilsk. And because of the permafrost thawing, the facilities like factories were damaged, and also diesel tanks were damaged. So we had leakage of diesel, what you can also see here. And the diesel is red, you can smell it, you can see it, you can even see it from the satellite pictures, right? But this permafrost thawing is damaging tanks that, yeah, with substances that are used for cooling, for cleaning, for many, many purposes in industry. And those substances might be, you cannot smell them, you cannot see them, and they might be very, very dangerous, for example, carcinogen. The question was here, okay, how can we now detect pollution? How can we detect For example, if there is some spillage of very dangerous substance without smelling it, without seeing it. And this is, of course, very costly if you try to put sensors everywhere. And even worse, what I learned from biologists and from people working in this area, you cannot just sense something. You have to know what are you looking for. So our approach was, and this was part of the GISTERA project, Wien Sustainable Watershed Management through IoT-driven artificial intelligence, is to observe a specific strategically selected points on the riverbanks and to try to find micropollutant source, because all these substances, they leave very, very small parts, very, very small micro fingerprints in the water. They are not dangerous. There are no health issues with it, but it allows us to collect these fingerprints. We can have expert knowledge analyzing that, trying to understand what could potentially be in this river. And then we use graph neural network. We create huge graphs. We work on different characteristics that water has, like viscoelasticity, and we create a huge in silico digital representation of the river. The idea here is that once we have this global watershed model, we can also create local watershed models that have specific characteristics here without having the large servers. And once we have these fingerprints, micro fingerprints that have been analyzed by authorities and human experts, we are then in a position to sense something very, very quickly. For example, if there is a spillage of some very dangerous substance. And the idea here is to detect these substances within minutes and also to infer upstream to be able to detect what is the source of the pollution, but also to infer downstream, to infer, okay, what could be the potential effect to drinking water supply, to agriculture, to human beings, to animals, to everyone, right? So this was the result of Swain project. We had we were not able to test that here at this river in Siberia, in Urals, because we didn't get any data, but we got data from Turkey, from Ergen Fluss, from Ergen River in Turkey. So we really tested our approach on real data. And we had here partners from Finnish Environment Institute, from University Wien, and also from Lugano. In our next project, we try now to deal with this limiting aspect, this problem. If you do chemical approaches, if you do dual spectrometry, you have to know what are you looking for. So you can only detect something in the water if you know what are you looking for. In Vienna, we are faced with changing environmental conditions. We have extreme weather conditions. And in Vienna, we get the drinking water from the mountain springs that are located here in this region between Niederösterreich and Steiermark. And the problem here is how can we detect on time, on the time pressure, not knowing what potentially can be in the water, how can we analyze the water and quality of water, how can we decide which of those 6, 7, 8, 9 springs can be used to supply a city of 2 million inhabitants with drinking water, which is really critical, super critical. An idea here is to use something fundamentally different. So we don't use here chemical approaches, we use optical approaches. We work here in this project. The project started this year, WWTF, AI-supported holographic environmental water monitoring, where we work with Boku, with Peter van Ostrom, who also was the founding member of Holoid company. It is a startup. And they developed holographic microscopy approach, which is a bit different to the traditional microscopy approach, where you have to adapt the focal point to see something. This is something you cannot automate. You cannot automate, and you cannot use it on a large scale. What they use holographic microscopy. Means they take snapshots of water. So you see these tanks where the water has to sail. So it has to be like quiet for 15 minutes. Then they take these snapshots of the water. And what you can see here, and these concentric rings here, can tell us about the objects in the water. And we have all kinds of objects in the water. We have sand, we have sediments, we have algae, we have bacteria, everything. Now, based on this shape, we can decide, or we can learn through AI what it means. And in particular, we can learn if this is dangerous. For example, if this is a bacteria, if it has DNA in it, this is super dangerous, because then it can be also, it can create health issues. So this is another way to show you how can we use this technology, holographic microscopy, but also AI. The project just started, we are working on it. How can we use these approaches to build a better world and improve nature and resources, how we use natural resources with the help of AI. Okay, so that's for my part. Today, I want to thank to my group, because everything what I have shown today is result of our group work. And I also want to thank all funding agencies who are generously helping me and my group to do research. Thank you very much for attending the presentation, and I'm very happy to answer your questions if you have any or some.
Thank you, Ivona, for this really very nice overview of the different angles of computational sustainability which you are following. Just looking into the group, if there are on the chat also, if there are any question. How much more expensive is quantum computing compared to classical computing?
Well, today I have to say that there is no application or real world problem where the quantum computer can outperform the classical version. As soon as we find an application or use case or a real world problem that outperforms the classical, there is going to be a commercial quantum machine. We don't have it yet. It is more expensive because of the overhead that we have with the classical machine steering and controlling the quantum machine. I don't say that this is going to stay forever like that. We are talking today about utilization of classical data on the quantum machine. You can utilize quantum data on the quantum machine, but we don't have it yet in real life, in real world, because our world is in classical data, right? So if we go into the direction that we have the quantum machine, then we have the quantum networks, quantum communication, quantum sensors, this might be the case. This might be very, very efficient, but it might be also the other case where we have this hybrid setup. Some part of the data is classical, has to be transformed to the quantum. We need a classical machine to steer it. So it depends where you are and where we'll be in the future on this spectrum between quantum, everything is in a quantum, or how much we have also this interaction with the classical, because this is overhead. This creates overhead right now. I don't know if this is answer to the question, but it explains why it cannot be answered that easily today.
Just as a follow-up, Where are you doing your experiments? Yeah, when you kind of use a quantum computer, you were mentioning also QuizKit. So where are you using your?
Well, usually when you use it today, you are going to use a simulator. So for every quantum machine, there are very high precision simulators that allows you to, I mean, look, when you are doing code development, I mean, you are debugging, you're doing all these things. This is super expensive doing it on a real quantum machine. So you do basically everything on the simulator. What we do, and I'm talking about research, we go on the real machine to get the numbers for the papers. Yeah, so this is always the last step because it's very expensive. So far, we have done it on IBM's machine, on different IBM machines that are available for everyone. We have also used the AQT machine in Innsbruck, and I have to tell you, every one of you can use this hybrid machine in Innsbruck. It is allowed for every student. I mean, of course, you have to attend some of the courses that have to do something with coding and utilization of quantum machines. But the machine is now also open for everyone. So the students can use it if you want to do a master study, if you want to do your master course, if you do some seminar, if you do some practical, whatever, everyone can use it. So yeah, and for the students, I think there are also commercial machines from Amazon and IBM that everyone can use it.
In the cloud, that you can use.
Yes, you can use it in the cloud, yes.
Just as a spoiler advertisement, no? You were mentioning if you want to do a master, there is an own interdisciplinary master curriculum, quantum information science and technology, between the faculties of physics, electrical engineering, and informatics. So if there is more interest, just look at the website.
Yes. And there is another lecture which is called Introduction to Computational Sustainability. So this was really introduction in computational sustainability. So if you want to learn more about this, there is specialized lecture where we look into the quantization, knowledge distillation, and all these models that all these tools and methods that you have for large language models. On the one hand, this is the first part. The second part is we try also to teach students how to utilize AI in the area of, I don't know, climate change, or how they can utilize it to build models, for example, for environmental protection, digital twins of rivers, watersheds, and so on. So these are the two parts of the lecture. Where we have the theoretical part, we have different lecture, but we have also the practical part where the students have to do some project work on the, sustainable IT, sustainable LLMs, and other. On the second assignment is to use IT to build a better world.
And which LLMs are you using?
Depending, I don't think that we prescribe that. The students can select pretty much everything on their own. What is available and what is feasible for the specific project work.
So last spoiler, the student should use then the Wien LLM, which is in fact an API. It's called Aqueduct. I guess you all got an email a couple of weeks or months ago, where you can then choose which open source LLM you apply.
Yes.
With the nice side effect that all your data stays at TU Wien. So you are not feeding the world with your data. Everything stays kind of in the scope.
Last year we didn't have that. This year, of course, you can use our own interfaces.
Yeah. So once again, since there are no more questions, Ivona, thank you for the presentation. Please, if possible, please share your slides with me and Marianne, communications team. And I'm looking forward to the next presentation next week, to see you and hear you all next Monday, where we hear something about sustainable security. So then we will see if there will be a trading between security and
I guess so.
performance, for
I guess
example.
so.
Ivona, thank you very much.
Thank you
And
very much.
until next time.
Thank you
Goodbye.
all. Have a nice evening. Bye.